Hi, this is the first tutorial in the Aromatic chemistry series, and this one is on the structure of benzene, which is this thing down here. So there's been a couple of attempts to show what benzene looks like and to determine the structure of it. So we're going to start with this model that was introduced by a man called Kekulé. So knowing that the molecular formula for benzene was C6H6, people were coming up with different structures for it, and the first sensible structure for benzene looked like this. So it's a flat or planar compound of carbon and hydrogen, 6 carbons, 6 hydrogens, and we've got alternating single and double bonds as you go around the ring. So 3 single bonds, 3 double bonds, and that would allow that one extra bond to form a bond to just one hydrogen to give you the correct molecular formula. So this is the Kekulé structure. Now we've actually moved on a bit from this structure, and we've discovered other things, which I'll go through in the next few slides, that have led us to a new model, but you do still see this model around. So if I was to draw that in skeletal formula, this is what it would look like. So something like that. So with every corner of this hexagon representing a carbon, every bond showing bonds between carbon atoms, so double bond between carbons, single bond between carbons, and then obviously with skeletal formula you don't show your hydrogens or their bonds. So this is actually very common, and you'll still see this, and this is still used by academics and people who are studying aromatic compounds and things, so don't be confused if you see this. It's still benzene, but we're going to show you another model as well in a little bit. Okay, so obviously the reason that we've moved on to a new model is that there were problems with the Kekulé structure, so I'm going to go through 3 problems with that idea of benzene having alternating single and double bonds, and tell you about how we've moved on from there. So the first one was the problem of shape. So if you consider single bonds and double bonds to have different lengths, single bonds are longer than double bonds, so we would expect a distorted hexagon, an irregular hexagon for the shape of benzene. So a single carbon-carbon bond is 0.154 nanometers in length. Carbon-carbon double bond is 0.134 nanometers in length. So that would lead you to expect Kekulé's benzene structure to look something like this, with shorter bonds, longer bonds, shorter bonds, and longer bonds. However, we know that it is a regular hexagon. So that's the rough shape of benzene, which means that it can't have alternating single and double bonds. Something else must be going on instead. Right, the second problem with the Kekulé structure of benzene is the type of reactions that benzene was known to undergo. So if you look at the Kekulé structure with its alternating single and double bonds, you would expect, because it's got double bonds, that it might react like an alkene does. Now we know from last year that alkenes tend to undergo addition reactions, where you take another molecule and you add those atoms in across the double bond, so the double bond is replaced by a single bond with the 2 new atoms on it. Benzene does not readily undergo addition reactions. So when benzene reacts, we do not get the double bonds breaking, we actually get substitution instead. So what we actually get is one of the hydrogens that's on these corners of the hexagon substituted and replaced by something else, and the double bonds stay intact. So the reactions of benzene didn't look like something that would have double bonds in it, so that didn't really make a lot of sense. So that threw into question the idea that there were any double bonds in benzene at all. Now, one of the ways that scientists got around this idea was to propose a new idea about benzene, that it was like the Kekulé structure, but that it had a resonance feature. So if this is Kekulé's benzene, it could look like that, or it could look like that. So the only difference is the positions of the single and double bonds have swapped. So scientists decided that perhaps it did look like this, but that these single and double bonds weren't fixed in place, and that there was a rapid equilibrium between these, so the bonds shifted and shifted back, so that you had this, then this, then this, then this. So this is called resonance, when the positions of single and double bonds alternate very, very rapidly. So scientists did have the idea that perhaps there was resonance within benzene, and that meant that there was no fixed position of a double bond, and therefore it didn't undergo the typical addition reactions that alkenes undergo. So we went from Kekulé to possibly resonant, but still with the Kekulé structure. But then there was still more problems with this idea. So the biggest issue with the Kekulé structure of benzene is its stability. So I'm just going to draw out some structures. Okay, so we know that compounds with a double bond in it undergo hydrogenation reactions to add hydrogen across that double bond. So this is ethene reacting with hydrogen to give you ethane. That happens very readily. Also happens with cyclic compounds. So this is cyclohexene reacting with hydrogen to give you cyclohexane. Now, when this reaction takes place, it's exothermic and there is energy released. So the hydrogenation of cyclohexene gives out 120 kilojoules per mole of energy when that takes place. Now you can use that figure to predict what the enthalpy of hydrogenation would be for the Kekulé structure of benzene. So you would expect that if you can hydrogenate cyclohexene, then you would also be able to hydrogenate cyclohexa-1,3,5-triene, also known as Kekulé structure of benzene. So you would need 3 equivalents of hydrogen to cross these 3 double bonds, and you'd get cyclohexane again. And because you're doing the same thing 3 times, you would expect the enthalpy of hydrogenation to just be 3 times greater. So you would be expecting an enthalpy of hydrogenation of about minus 360 kilojoules per mole. Now it's just worth pointing out, in your exam, if you're asked about this issue with stability, they may not call this the Kekulé structure of benzene, they may call it the theoretical molecule cyclohexa-1,3,5-triene. So it wasn't proven to exist in this structure, it's just a theoretical idea, and obviously under UPAC guidance you would call this cyclohexa-1,3,5-triene because it's got 3 double bonds in it. So don't be confused by this, it is just this, the Kekulé structure of benzene. So if we hydrogenate benzene, you do not get an enthalpy of hydrogenation of minus 360 kilojoules per mole. You actually get about 208 kilojoules per mole released. So it's miles out on what you'd expect. It's about 150 kilojoules per mole lower in terms of energy release than you would expect. So I'm just going to draw this out as an energy level diagram so that you can see it as it may be shown to you in an exam. So you may see something in your exams that looks something like this. So this is showing the amount of energy that each of these compounds has and the difference between one compound and cyclohexane. So cyclohexene is higher in energy than cyclohexane. So if you were to hydrogenate this compound, you would release 120 kilojoules of energy per mole to get to this. Now, you would assume that if you've got 3 lots of those double bonds, Kekulé structure of benzene, cyclohexa-1,3,5-triene, if you were to hydrogenate that, because it's very, very high in energy, you would release 3 times the amount of energy as this one. So you'd have minus 360 kilojoules per mole enthalpy of hydrogenation to get down to here, to the same compound, cyclohexane. What you actually find in experiment is if you take benzene and you hydrogenate it to get it to cyclohexane, actually only releases minus 208 kilojoules per mole of energy. So the actual benzene structure is lower in energy than the Kekulé structure would suggest, much lower, about 150 kilojoules per mole difference in their enthalpy of hydrogenation. So there's a very clear issue here with the structure of benzene looking like this. But moving on through time, scientists discovered that the nature of a covalent bond was that it was essentially a shared pair of electrons. Once we start looking a little bit closer into electrons, we can start making better, more accurate predictions as to what the structure of benzene is actually like. So to show you what we currently use as our model, we move on to the next slide. So the current model of benzene is all based around the idea of electrons and electrons sitting in orbitals and those orbitals being able to overlap. Okay, so around each carbon atom in a benzene molecule, there are orbitals where electrons can be found. So for each carbon atom, the electrons can be found in these 3 hybridized orbitals. So these orbitals are made from s orbitals and p orbitals joining together and hybridizing. So these are called sp2 hybridized orbitals because they're made from 1 s orbital and 2 p orbitals. Now if each carbon's doing this, you can see that there's a trigonal planar area where electrons can be found. So that leads to our hexagon. Like this, planar hexagon, so you can find electrons here, here, here. They're those three sp2 hybridized orbitals. And there's also a p orbital above and below each carbon atom. So as we're looking at this diagram here now, the p orbital will come towards us and point away from us. So it sits above and below the plane of the ring. So if we draw this in a different orientation. So if you're looking kind of to the side of a benzene ring, you can see the p orbitals, these dumbbell shapes, above and below each carbon atom. Now what we believe happens in benzene is that these p orbitals overlap with each other. So these overlap, 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 like that, to form a ring of space where electrons can be found above the ring of carbon atoms and below as well. So there's a ring of area where we might find electrons below the benzene ring as well. So it's kind of like a weird sandwich shape where you've got area where electrons can be found, 6 carbons in a ring, and then an area where electrons can be found. So turning this back into a bird's eye view, we now draw benzene as the 6 carbon atoms joined together by covalent bonds, all single covalent bonds, and the spare electrons are delocalized around the ring, and we draw it as a circle. Obviously we've still got the hydrogens there as well. These can be drawn in or they can be omitted, it doesn't really matter. So this is the modern view of benzene, that each carbon atom, each carbon-carbon bond is equivalent, and each carbon is making 3 bonds, and the 4th electron, the 4th valence electron from each carbon atom, is delocalized into these rings of area where you could find electrons, which are represented by the ring through the middle of the hexagon in the new structure. So we should now see benzene drawn as a hexagon with a ring inside, but we do still sometimes see the Kekulé structure. It's just kind of stuck around a little bit with scientists and academics. So both of these are representing this ring of delocalized electrons. So for the rest of the topic on aromatic chemistry, we're going to look at the reactions of benzene, which we know aren't addition reactions as you might expect from looking at this compound, but they are actually substitution reactions where this ring of delocalized electrons remains because it makes the compound very, very stable. Now, if you would like to know any more about these orbitals, the hybridization of orbitals here, I can save that for another tutorial. If you let me know, I can do that, or you can have a look at something like ChemGuide or other tutorials. But I don't think it's essential for this at the moment. As long as you are aware that we've got this ring of carbon atoms with 2 rings of delocalized electrons above and below the plane of the benzene ring, then that is your structure of benzene.